So, you know, if you're using object store or something like that, you still have to say this class or this instance of this class, please record this on in some kind of persistent store. Otherwise, it's just a transient data structure. So, to summarize, the OO paradigm. The objects export a set of behaviors. The application supplies the data. So when it instantiates this object, it says, okay, based on this relatively static behavior, here's some data. Please, I've now created this object. Please behave in the way you wish. If you want different behavior, you need different objects. You need to create new classes. So that's the end. So there's object. So that's my quick rundown on object-oriented programming. This isn't fundamentally an object-oriented programming class, so I wanted to set some ground rules. Questions, comments, thoughts about that? Cool. Okay. So now on to the relational model. And this is a database conference. This is a little more interesting to everybody. So these are rules from E.F. Codd's book. So the information rule. Basically, everything's a table with rows and columns, and there's nothing else. That's there are no other interesting data points in the database besides the things that are at the intersections of rows and columns in a particular table. That's his rule. When you change an application, when you make changes to the underlying representation, the application program shouldn't have to care about that. It can still access it in largely the same way, but you know, the select will work no matter how you've hammered this particular thing on disk or what implementation you have. Cool. And changes and he's a little unclear actually in this rule whether it means changes, but generally, the more changes to the database, except in so much as the application is expecting those changes, shouldn't change their ability to work with the data. And this kind of sounds like exactly the opposite of what we talked about, or close to it. So in the relational model, data is primary. The relational database stores the data and makes it available to the application. That's what it does. It doesn't know or care about the applications that access it. It provides a data access API, and the application is struggling with it. It doesn't know or really care what happens to this data. Yes, modern databases all have ways of moving application logic into the database, but from a conceptual point of view, these are not fundamentally application objects. These are ones to support the data storage model. So store procedures, you know, got it. Which is to say, the behavior it has is data-centric, not application-centric. As an application optimization, sure, people shovel application and business rules into the database all the time and store procedures. But conceptually, for example, a trigger is there to ensure data integrity in the data model, not to implement the application. Obviously, that's a fuzzy area. You can quote any number of applications that have moved business logic into the database. Be right back. But from a conceptual point of view, what the database does is it stores the data, and it doesn't care what the application is about. So we talked about relationships in the object model, so let's talk a little bit about relational relations. I guess relational databases are about relations. An RDBMS has no predefined relationships. Just categorically state that. There are no predefined relationships at all in a relational database. Foreign keys are not predefined relationships. Foreign keys are declare integrity constraints, but they're only secondarily about relationships. Obviously, this microphone and I have much to learn about each other. Let's try clicking it on a little further here. Much better. Okay. Foreign keys fundamentally are about integrity constraints. If this record only has meaning if these records exist, or this field, don't allow this field to fail to refer to another one. But there's nothing that it does not. Foreign keys do not exclusively define all the relationships in a database. Frequently, they don't even necessarily optimize any more than an index would access to them. You can join any way you want in RDBMS, even if it makes absolutely no semantic sense whatsoever, as long as you can make it work semantically. Foreign key relationship may optimize it, an index may optimize it, but that's an optimization. That's not fundamentally about the. I think we have a weak clip here. this. Stay, thank you. So what's important about this is you make up the relationships at runtime. There are no static relationships like this in a relational database. If you have a hierarchical database or some other architecture, that's different. So the relations themselves are dynamic. By relations, that's a fancy term for the general case of a table. So Postgres uses this term frequently. It's somewhat inconsistently in the documentation about a relation versus a table. But for right now, think of a relation as the general case of a table. So we have these two different statements. Conceptually, these both do the same thing, which is create a relation. One of them creates one that lasts a while, unless you put temporary at the end. One of them is extremely transient. It only lasts until the data has had a chance to get back to the client. But there's nothing logically different about them. You can take this and embed it and use it like at any table, and it just throws it away at the end. And you really can't have an RDBMS that works without doing this. This is basically what RDBMSs are about in the relational model, is creating and destroying these virtual transient relations all the time. So, databases kind of don't make much sense without persistence. It's, with all due respect to the NoSQL people, kind of if you restart the machine, you kind of expect to get the data back that was there before. Depending on, so the default operational model is let's store the data and get it back to you. Temporary and transient data is kind of a special case. It's the results of a select. You have to specifically declare a table as temporary. There are views which are relations that are calculated on the fly. But the basic operational model is hammer the data onto the disk. So those are the two worlds. You have in objects, you have a mostly static typing system with an extremely dynamic typing system for relational databases. You have encapsulated data in the object model versus exposed data in the relational model. You have bound behaviors in the case of the object model versus external behaviors in the case of the relational model. The bound behaviors are bound into the object in the OO model. In the relational model, the behaviors sort of trundle up and see what data are available to them. Explicit persistence versus assumed persistence. The explicit persistence of the OO model, you have to say, okay, save this for me, please. As opposed to the relational model where simply creating a table, you're implying persistence. So, and the problem is ORMs were designed to bridge these two worlds. And we'll talk a little bit about why and the history of how we got here. And with varying degrees of success. And different ORMs approach this problem differently. So we'll talk a little bit about how about the different ways ORMs handle this kind of bridging. There are two general families of ORMs. There's the RDB MASUP one, which is the slightly older one. Hibernate is an example of this, where it was designed to work on existing databases. And then there's the application down one, where